Hello, my name is Matt Stewart. This is Bob Davidoff with Bentaus. Thank you for joining us this afternoon as we talk about one of the hottest topics in our industry. AI is scaling faster than anything in data center history, but the grid is not necessarily scaling in the same way. See, traditionally, data centers have acted like heavy static loads, right? They've had to deliver the 99.9999, all the nines. But things are changing. As AI factories grow and scale to gigawatt size, grid volatility still exists, right? Grid operators are still dealing with congestion, with weather, with renewables. What the grid needs is not more static load. It needs fast, controllable load. And so the question that we asked was very simple. What if AI factories could respond like a grid asset? Something that was dispatchable, something that was controllable, something that was responsive. See, GPUs already have fine-tuned power control. Data centers already have the telemetry. What was missing was that orchestration, that coordination, right? That closed-loop control system that tied it to the grid. We didn't invent new hardware. We just took existing behavior and we tied it to the grid.
Well, thanks, Matt. I'm going to talk a little bit on what Matt was just talking about and how it works. As Matt was saying, it starts with the grid. And what are we doing with the grid? Well, for the first time, we're able to take signals. Well, what signals are we taking? These things are called demand response, emergency response, a price response. Well, what does that all mean? A demand response can say, hey, it's really hot out. We're 2 to 6 p.m. and those ACs are cranking. And then what we need to do is we'll get a signal from the grid saying, hey, that big, large load, as Matt's saying, can you guys curtail or rev down all those GPUs for us with this signal? And that's when the magic happens, and this is where we bring in that orchestration layer. And that orchestration layer now takes that signal, and then we get to have a little fun. Well, I think it's fun, because what do we get to do? We get to ramp up and ramp down those very expensive GPUs. And so those GPUs that we're ramping down in those AI factories, now for the first time are communicating, and AI factories are becoming this novel idea of VPPs, virtual power plants. And we're able to become these grid assets. There's a lot of telemetry that's included in here. So we're obviously monitoring heat. We're using redfish standards. We're talking with a lot. We're creating this feedback. And we say, hey, grid, we took this signal. We orchestrated. We basically curtailed, slowed down, throttled down those GPUs to give back that energy. And then we get to respond back to that grid and that closed loop system and say, hey, yay, we did it. What's next for us? And so then we could go on to the next slide to talk about the methodology. So how do we do this? Well, a lot of times things start in a lab. And what we did, and I want to give a lot of thanks out to Kevin Kolp. Without him, this couldn't have been done. He allowed us access to a Supermicro lab, and he entrusted us to not burn it down. And so what did we get to play with? We got to play with a lot of B200s. And in this demonstration, we worked and proved it with the B200s. But since then, we're allowing AI factories to be GPU agnostic. So it's not only just NVIDIA, it's AMD, it's even the Intel Gaudis. And so this is where we're using this with OEMs like Supermicro, and then revving up and ramping down NVIDIA, AMD, Intel, and then taking those grid signals and now having real-time GPU modulation. And to add to that, 3 important facts. You got to take into consideration, and a lot of you guys in here probably already know, that thermal side, those things get really hot, and you got to control that. And then now we're all moving to 800 VDC and handling a tremendous amount of power. And so that's on the data center side. But then what about the client? This is where, how can we still come up with a solution that can do SLAs or service level agreements? So when you're throttling down and not stopping those workloads or shifting those workloads, and meeting SLAs by just throttling down and slowing down, at the same time keeping the data center happy, at the same time keeping the grid happy. You have three major stakeholders here that we have to address.
So here's what we found in the lab. And this is just 3 examples of different tests that we ran. But the entire time, from ingestion of the signal to the orchestration to the GPU power modulation and then sending that confirmation back, it averaged about 19 milliseconds, right? And so we're talking very fast, and actually faster than some of these grid services that Bob mentioned require. That's critical because grid operators, they don't need just a fast response, they need a reliable response. And that's what we found. We found that across multiple tests, whether we were curtailing 30%, 70% power on the GPUs, it was bounded, it was predictable, and it was repeatable. This is another illustration of that, and this is end-to-end response time from grid dispatch to power reduction to confirmation, like I said. The majority of that being the GPU power modulation. Funny enough, the orchestration was so quick, we had to fudge this a little bit just so it would show up. It was very, very, very small. Again, this means that AI infrastructure can respond faster than required for these grid response programs, and within the envelope of high-performance grid assets like battery, BESS. So this opens up participation in grid services that weren't previously considered for data centers.
I want to add one last thing there, what Matt's saying, to put that 20 milliseconds into perspective and to keep saying that word fast. Well, what does that fast mean? 20 milliseconds is 2.5 times faster than the fastest battery for fast response. There's a lot of fast in there for you guys. But so the only other grid asset that's out there that can handle a fast response to the grid is a BESS, is a battery based on frequency. And here for the very first time, we can say AI factories, now we can also be that fast acting, responsive, and doing it 2.5 times faster than a battery. So to go back to just saying, well, that grid asset. Well, now since AI factories with technology and innovation can now become a grid asset, we can provide grid services. And so what are some of those grid services? Some of them are, well, now we could be this demand response participant. Well, what does that mean? Well, that also means that now we can drive revenue and money. Since we have that capability of doing those milliseconds responses, we could get paid for that by throttling down into the grid. And then now, since we have a closed loop system where we're giving signals back and saying, hey, grid, we got your signal, we orchestrate it, we ramp down those GPUs, throttled down them, and said, and get the response back to the grid. This way, now we can act as a load balancer and add grid resiliency. And then now, since we give the grid confidence, these AI factories in these data centers, where a lot of them out there right now, and as we're going through ourselves even being a neo cloud, to get approval for that amount of power, you need to give the grid, those RTOs and the co-ops and the utilities confidence to say, well, hey, if we need that power back, can you give it to us? Which then we say, yes, we do. We have systems now, we have orchestration. Then it allows us to have faster interconnect approvals because now there's less volatility and there's less fear in there to award that power.
Yeah, so what does this mean, right? Like Bob's saying. Well, it means that AI factories don't have to be a problem for the grid. They can actually be part of the solution. Data centers don't have to be that passive consumer of power. They can be a controllable grid responsive asset. All while using systems that exist today, by the way, right? This has immediate real world implications, right? Everything is in line and in place. So, like Bob mentioned, one of the biggest blockers for AI deployment is interconnection approvals, right? But if AI behaves like a controllable load, it can operate within constrained transmission markets. It reduces pressure to add new generation. And so it becomes easier to approve for interconnection. This is how AI scales within the grid that we actually have today. So AI doesn't just need power, it can help manage it. The question now isn't whether it's possible, it's how do we standardize it, right?
And when we standardize this, this is not just us. It's exactly why we're here today. It's a community. It's OCP driven. So this is where we would love to be able to continue to look for those partnerships, look for those collaborators, look for those integrators on here. And we're around and we'd love to be able to showcase this and what we're doing and work with future groups out there. And it looks like we got about a little bit of head of schedule, seems today.
Yeah, we've got 3 or 4 minutes for any questions if anyone has any.
Doesn't matter, I speak loud. My question is around stability. You said you could potentially improve stability with these systems, but obviously being tied to the grid, you also have the risk of instability, introducing instability into the grid. And anything that's grid tied is controlled, is governed by cybersecurity requirements and things like that. And I'm just curious if you've looked into that at all.
I'll take this one, and it's a great question. And we've looked a lot into grid security. Grid security and grid resiliency is a really big topic. Let's just, I can't give all the cards away, but let's just say that we're really working on the security piece in our EOS software to address that. There's a lot of vulnerabilities in the grid. And then when you can literally look at another tangible or intangible value of an AI factory is the what if out there. Not only can we modulate those GPUs, but what if an AI factory can act as an energy shield to help protect the grid? And those are some of the next iterations, and looking forward to maybe being on stage next time to talk about that one.
I had one question. I think this is super nice work. We are now busy with DC distribution within the data center, and I think in DC grids, typically we also want to have like this droop control, demand response, and things like that. I think it will be very interesting to do this also non-communication based, but basically just based on the voltage in your grid, so that you can see, our voltage collapses, how fast can we respond? Because in that way you can also make a very robust response, and I think it's a very essential part there as well. I was just wondering, did you already think about that as well, or was so far your focus mainly on the communication-based approach?
Yeah, I'll also take that one. It's another amazing question we have in that orchestration. When we talked about that telemetry side, we are taking all types of e-meter data, all types of voltage, all types of amp, as much data as we can. And as things are moving over into that 800 VDC, and right now, with those AI transients that are coming in, spiking those loads, and then one of the solutions today is, here's a power shelf, and here's a battery, here's a UPS, as we can basically harmonize or cleanse that or handle and technically act as a shock absorber. But what if we can get ahead of that also with software and dampen and throttle down and work on things? Here's something I will let out, the cat out of the bag, is that using that modulation, we could do things as a GPU soft start. So this is where we can literally go at the BMC level and say, hey, look, as these things are ramping up, instead of 750 watts or 1,000 watts, we can start to power cap these, leveraging the modulation technology. I think we got time for one more question.
I don't care. Okay. Thank you again for the interesting talk. One question about the latency and the 200 or 20 milliseconds that you guys mentioned. From my point of view, it's still a recent issue for DSOs and TSOs with communication latencies of, for example, substations. And the times that you are proposing right now are relatively fast. And if I think about the communication latencies for digital substations, for example, they are much smaller. So is the data or the timing that you present kind of isolated to the data center itself? Because I would assume that gathering information from the rest of the grid takes much more time and could be an issue due to latency. Thank you.
Yeah. And you're 100% right. I'll answer this question as quickly as possible. That's still based on a lot of SCADA technology and Modbus technology, especially SCADA. And to your point, the latency is there. And so when we're tying into this, we're tying into something called a CSP, or a curtailment service provider. That's when we're starting to work in things that are way more API driven, and using things like MQTT, which is very low latency. And then we use some of the other technologies, and then incorporating it into Redfish, and then using those APIs and going more into that MQTT, and then also into our technology on our data pipeline for low latency. So when we send the signal, it's required to be 2 seconds. So we're beating that within 2 seconds, because to your point, to take it around because of some of the older communication protocols in the grid, we need to do that within 2 seconds. So we're way ahead of that curve, and then this is where hopefully we can continue to innovate that energy side, not just the DSIM side, to be able to push further in to take that technology and those frameworks and those standardizations and push it further out into the grid. Thank you very much, guys. I think that's all the time we have. Yep.